Hello, 5th grade. This is our lesson for 13.3b, the second half of the lesson that we started yesterday, which looked at right triangles and the special relationship that their angles have. Today we're going to extend that by looking at two more different types of triangles, isosceles and equilateral. As a quick reminder, an isosceles triangle has two sides that are equal to each other, and an equilateral has three sides that are all equal to each other. We'll look at each of those in turn, but we will start by looking at isosceles. And actually, before we look at those, we're going to look at some cutout triangles that I made. These are both isosceles triangles. Right now I have the third or different length on the bottom, so these two sides are the same, and these two sides are the same. The angles that we're going to want to focus on are these angles. Let's see if they actually give us a vocabulary for that. Yes, so down the middle of each of these, right down the middle of the side that, I know there's a lot of glare, so it's a little bit hard to see. Do you see that line that I drew down the middle? It's in the middle, not on either of the two equal angles, but the two others. It's the line of symmetry. When you draw that line, both of these triangles, even though this one you can see is a right triangle and this one is an acute isosceles triangle, both of them are identical on either side of this line. And I could actually prove that if I wanted by folding it in half. And you'll see that I can fold it perfectly so this angle lies right on top of the other one. They take up the same amount of space. Similarly, this one right here, when I fold it right down that middle, that line of symmetry, those angles are exactly the same size. If you don't believe me, I would challenge you to draw any isosceles triangle you can. Remember, isosceles means that both sides are the same length. And you're going to find that each time when you fold a paper over, that these angles are always going to be equal to each other. Now that's our property with isosceles triangles, is that these opposite angles that are opposite of the equal sides, do you see that? These are the two sides that are equal, and if I point to the angle that's most opposite of those are the two that are equal to each other. Just like here. The two equal sides, if I drew an arrow across, those are the two sides that are equal to each other. Okay? You can use a protractor to measure that when you draw your isosceles triangle. It's up to you. But what I'm going to do with the rest of my time on isosceles triangles is I'm going to show you some examples of how we can use that principle. So these are isosceles triangles. You can see that these are the sides that are equal to each other. Think about those little arrows I just talked about. If that side is equal to that side, how big is this angle? 62 degrees, because they're equal to each other. Can I figure out what this angle is? Well, if all three of them together have to be 180 degrees, 180 degrees minus 62 degrees minus 62 degrees, or 180 minus 124 degrees, is equal to 56 degrees. Yeah, that angle looks a little bit smaller, so it seems to check out. All right. Ooh, this one's a little bit harder. They give me the third angle. Do you see how this is not the angle that's equal to either of these? Because this is the angle that's the opposite of the different length. But these two sides are equal, so these two angles are equal to each other. But I don't know what either of them are. Is there a way I can figure this out? Well, actually, if they're equal to each other, I could label them the same thing, right? They're both equal to, let's call them x. I don't know what x is yet, but together, they're equal to each other. So 78 degrees plus one of those plus another is equal to 180 degrees. This should start to look a little bit like algebra to you. I'm going to combine like terms. 78 degrees plus two of those x's is equal to 180 degrees. If I subtract 78 degrees from both sides, I'm running out of room, so I'm going to move up here. If I subtract 78 from both sides, 2x's is equal to 102 degrees. which means 2 something. 2 times some number is 102. Or if I just divided 102 into 2 different groups, I can find out that x is equal to 51 degrees. Does that number work though? 51 degrees plus 51 degrees is 102 plus 78 is 180. It does. This is 51 degrees. Okay, let's move on to this next one. If you're following along, this is on the bottom of page 200 in your book. Let's figure out what other angles I can solve here. Well, this is a right isosceles triangle, right? So this is 90 degrees, which means these two are opposites and they have to be equal to each other. And from what I just found out, it's a right triangle, which means these two angles added up have to be 90 degrees. So let's label that x. Two x's have to be equal to 90 degrees, or each x should be 45. Because 45 plus 45 is 90. They're equal to each other. Seems to check out. And if this is actually a right angle too, if that's 45 degrees and I cut this in half, that would be 45, and that would be 45. And 45 plus 45 is 90, which makes a right angle. Okay. And then next one, this one's a little bit tricky. I made a little mistake actually while I was drawing it. This triangle right here, the smaller one inside, is my isosceles triangle. So these two sides are equal to each other. What we're trying to figure out is this length. Well, or this measure, sorry. The big triangle I can see is a right triangle, right? So if this is 42 degrees plus something plus 90 is 180. So whatever this angle down here is, plus 42 has to be 90. That means this one has to be 48 degrees. And if this is an isosceles triangle in here, opposite angles are equal to each other, 48 degrees. This one also has to be 48 degrees. Which means 48 degrees plus 48 degrees is 96 degrees. This angle plus 96 has to be 180. So what this is missing is 84. So there's my answer for that one. Okay? If you have more questions about isosceles, you'll get some practice on your homework, but let's move on to one more type of triangle we haven't looked at yet, and that's an equilateral triangle. Now, an equilateral triangle actually kind of looks like an isosceles, right? If I didn't have this side, I'd say these two are equal, and these angles are equal to each other, right? But if I flip my paper like this, well, these two are equal, so these two are equal to each other. Or if I flipped it again, these two sides are equal, so these angles are equal. Hopefully you're not too busy at this point. But if I looked at this as an isosceles and these two are equal to each other, let's call both of these x, right? Because it's an isosceles triangle. And then from this angle, if I look at these two, well then this is also equal to it. And then all three of these angles have to be equal to each other. If the lengths are the same, these angles all actually end up being equal to each other as well. And that's another thing I invite you to explore. Every time you get a ruler and you make a triangle that has all equal sides, all the angles will also be equal to each other. I drew this one to scale, so you can use a protractor in a minute to find out how big it is. But first, let's see if we can figure it out on our own. What do all three of these angles have to add up to be? Just like any other triangle, all three angles added up are equal to 180 degrees. So 180 degrees is equal to x plus x plus x. All three of them together. And they're all the same, right? So they each need to take up an equal amount of 180. Or 180 degrees equals 3 of those x's. If I divide both sides by 3, 180 divided by 3 is 60 degrees. Let's see if that's right. Use the protractor. 60 degrees. I could go around and measure all these, but they're all going to be 60 degrees. If I added them all together, you will see that equals 180. If you cut this out and you fold it on all the different angles, you'll see they're all the same size. So there's our other property. With equilateral triangles, all of the angles, are equal to each other. Why is this useful? Well, let's look at some examples. I'm so glad you asked. These are the problems on page 202 in your book. We want to find this angle up here. And we see from these tick marks that all three of these are equal to each other. So that means that this is 60, this is 60, and this angle up here is 60 as well. We also see that this smaller triangle on this side is a right triangle. So if that's 60 degrees, whatever x is plus 60 has to equal 90. So what does x have to be? 30. And I could actually do the same thing on this side, couldn't I? 90 plus 60 plus 30. Oh, and 30 plus 30 is 60. We already knew that angle was 60, so that seems to check out. One of the reasons I love triangle problems is there's lots of ways to check yourself when you fool around with the numbers. So even though I didn't need to find this one out, that gives me a lot of confidence in my answer. So I'd always explore you to play around with the numbers, see what else you can learn. All right, this one they're asking for two different angles for us to figure out. Here's our equilateral triangle. So right away, I know that all of these are 60 degrees. Well, actually, x is pretty quick to figure out, isn't it? Because that's an angle on a line. So 60 plus whatever x is has to be 180. So 180 degrees minus 60 degrees equals 120. Yep, that's obtuse, that's obtuse. Do you see how I use an old concept that we learned before about angles on a line? And that really quickly solved that for me. I can use triangles, and that's also going to help me prove that, but don't forget about the things that we've already learned in math class this year. That made that a pretty simple thing to figure out. If this is a big old right triangle, and this is 60 degrees, and that's 90 degrees, then whatever this angle is plus 60 has to equal, 90. So 60 degrees plus y equals 90 degrees. Or if I subtract 60 from both sides, y has to be 30 degrees. And there's, again, multiple ways to check this out. This right angle right here, that has to be 30 degrees, doesn't it? Because 30 plus 60 is 90. And if this is 30 and that's 30, then that's 120. Yep, those all add up to 180. Actually, this ends up being an isosceles triangle, doesn't it? Because these two angles are opposite of each other. All right. And then the last problem for us to look at, we want to find this little angle right here, x. I didn't mark it, but this is also an equilateral triangle. So all three of these are equal. Let's go ahead and mark that real quick as a reminder. 60 degrees, 60 degrees, and this up here is 60 degrees. Well, if that's 90 degrees, then this has to be 60 plus 90 plus 30. This is 30 degrees. And if this is a right angle, then 30 plus that has to be 90. That's got to be 60. And I can see that this is also a right triangle, 90 degrees plus 60. That's got to be 30, and that's half of. There's lots of ways. I hope you're starting to have some fun with these as you play around with the numbers, and you can see how the right triangles, the equilateral, and the isosceles all help each other out, as well as the angles on a line. So if you remember all the different pieces to this, hopefully it's a pretty simple and can even be a fun thing to work through. Think of them like little puzzles. Your homework is 127 to 131, which sounds like a lot, but there's lots of big triangles that take up a lot of space. So I'm sure you're up for the challenge. Thank you, 5th grade, and any questions that you have, you can ask me during our Zoom session tomorrow.